So, yeah, I wasn't sure what to do for the tutorial. I guess for our group, our expertise is probably more on the experimental side. So, I just put together some these things that, I guess, very specific things that, I didn't know how to do. They might look basic to some of you, but at least I think it will be good, tools to have for experimental chemists. So I kind of have like three, small things that I want to talk about. So the first is substructure filtering. So basically, if you have, a data set of molecules, how do you filter them based on kind of a predefined filter of substructures? The second one is, with the same kind of data set of molecules, how do you find the common substructures? And then the last one is, how do you query data from PubChem? These are all the things that I didn't know how to do, but I end up, discovering that they are pretty important and, just pretty nice tools to have. I will share the code later. You can take a look at the details, but, I just want to kind of, talk about what each of these, do and kind of show you, in general how this can be done. So for molecular substructure filtering, so basically the idea is you are filtering a data set of molecules, you are discarding the molecules that matches your substructure filters. So these are, probably the substructure that you don't want in your data set, right? They can either be, reactive or interfering with, whatever assay or property that you're looking for. So, in terms of the code, these are just kind of very basic illustration of, what can be done. So you load some molecules, you can draw them out, see what they look like. And so the first approach you can do is there's these, kind of predefined filters already implemented in RDKit. So this particular one is called paints. So paints is a pretty important filter. This filter kind of filters out, a lot of substructures that interferes with biological assays. So these are either, structures that can be reactive or they are compounds that typically have colors. So they interfere with some of the fluorescence assay. So the paper is right here. You can check it out if you want the details. So basically, in terms of how to use it, this is actually pretty straightforward if you kind of figure out how do you, write these things with RDKit, which is, can be kind of confusing at times. So basically, you just load the filter from RDKit, this predefined paints filter. And with your data set of molecules, basically what you do is you just, get the match. So you go through every individual molecules and you're trying to match with the substructure filter. So here you're just getting the first match. So whenever you got a match, you just kind of, stop the thing. Basically this is just a loop and you keep matching the substructure filters. And then you end up with basically two sets of molecules. One set is molecules that, did not match any substructures. One set is molecules that match at least one of the filters, right? So the concept is pretty easy. So, you can sort of draw these out, the molecules that matched one of the substructure filters. So you can draw these out and see what the filter name is, kind of what substructure it matches. You can see these, quinones here, indoles, catechol. So you can kind of see what sort of substructure they matched and, what they are essentially. So that's, using kind of RDKit implemented substructure filters. So the second approach is, you can also use your own list of substructure patterns. So you can, define these in smarts. So you don't have to use kind of a predefined list. So this filter is from this paper right here. And this filter is actually also implemented in RDKit, but just for the sake of, showing how this can be done, we're just using kind of a list of smarts patterns and then trying to use that as our filters. These are just kind of showing, what some of the smarts patterns are. And right here, I'm just drawing out, some of the smarts patterns, substructure filters. RDKit has issues with rendering some of them. So these are the ones that you can actually draw out. So in terms of actual filtering, it's, the basic idea is still kind of the same, right? You just go through like molecule by molecule and trying to match with the substructure filter that you already defined. So the only thing that's kind of different is that, here you can kind of match it, either do first substructure match, or you can just try to match all of them and see what they look like. See if you can, however many substructure filter you can match it with. But the basic idea is the same. You're just going through molecule by molecule and then comparing it with the substructure filter that you defined. So just kind of show you, some of what the results can look like. So here's some code that, draw out some of the molecules and match the substructure filter. And then you can actually, from the matching process, you can get, the structure that matched with the filter and, kind of highlight them. So it's a nice visualization to see what some of the substructures are in kind of these data set of molecules. So here is just 5 of them. You can see the kind of the substructure that you probably don't want in whatever data set you have. So that's the first part, substructure filtering. So the second one is actually kind of similar. So basically this is kind of find common substructures. So still you have kind of a data set of molecules. You're trying to find, what is the common substructure of these molecules. So yeah, basically, here is kind of a algorithm that's implemented in RDKit. So the basic idea is, you from the data set of molecules, you kind of choose one as query, all the others as targets. And then you're just kind of going through the query molecule, going through the substructures, and you convert it to smarts and check if this substructure is in all the targets. And then basically you're just picking the biggest one. And then there's a lot of, I guess, speed ups that you can do to make this a lot faster. But this is kind of the general idea of how do you find the maximum substructure. So again, just kind of, talk you through like what, each of these code block do. So basically, you kind of have these molecules that, I use for demonstration. And then you use kind of this algorithm that's already developed in RDKit. So this is kind of how you use them. Basically, you just do find MCS for all the molecules. And then you can kind of draw out, what is the maximum common substructure that you can find in this data set of molecules. So this is kind of the smarts pattern that I found with these molecules. And then you can kind of, draw it out. Basically, these code just kind of draw some of the molecules and then highlight the common substructure. And these kind of, you can take a look later if you want. They kind of align it with the substructure. So the orientations are the same. So it's kind of a nice visualization. So everything is pointing in the same direction. So it's easier to see. So that's kind of the default threshold for these. So it doesn't have to be very strict. It doesn't have to match kind of 100%. So if you set a lower threshold, you kind of like have a bigger common substructure. And then you can also match it with, ring only. So if you, kind of define that, you kind of matching it with rings. So some of the long chains, it doesn't get matched in the ring. So ring only matches rings. So that's kind of nice to have. So these are just some of the, I guess, functionalities that's kind of defining RDKit also. Just at least I didn't know how to use them. So these are some of the things I thought would be kind of helpful to talk about. The very last thing I want to talk about is also something that seems quite basic, but I also wasn't sure how to do. So this is just kind of querying data from PubChem. So PubChem kind of has this like URL. You can just send these like URL queries to PubChem. They kind of have like a kind of complex format. When you actually get to know it, it's actually not that complex. You just kind of have to know how to structure it. So you kind of have this thing, and then you kind of have your input, what kind of information that you have. So it's for chemical. If you're querying a chemical, you can either use name, PubChem ID, or smiles. And then you need to define the output of whatever you're querying. What do you get it? What's kind of the output format that you want it to be in? So that's kind of the basic idea. I think these information is also on the PubChem website. So here is just kind of a example of how you do queries. So you have this chemical, you kind of query it by name. And then, you send a query to PubChem, you get the response. So if this is like in the actual piece of code, you might want to like catch some of the response that it gets, right? If it's a 4,4, you probably want to kind of skip that molecules and so on. But the basic idea is, you kind of just have to structure this URL in a way that PubChem can recognize, and you just kind of have to know kind of the structure of it. And then once you kind of understand that, it's quite nice to have. You can query a lot of chemicals with PubChem. So this is kind of query by name, and then you're just finding the molecules, and then this right here, you're just kind of with the PubChem ID, you can query different property of the molecules, for example, molecular weight, and then you can see get a nice response here with the molecular weight of the molecules. And then, you can get the structures, and then, here you can see the structure of the molecules drawn out. And the very last thing I want to talk about, so this is something I use a lot, PubChem Pi. So this is kind of developed, I think, by a few people, and then unfortunately it stopped around 2017. But the nice thing is it doesn't have any dependencies at all. So you can kind of modify it, and you can still use it and kind of modify it to whatever purpose you want. Like I try to modify it so that I can look up PubChem with CAS numbers, which is always kind of annoying to do. So just kind of so PubChem Pi is essentially they do these queries under the hood, so it makes it a lot easier kind of in terms of the actual syntax. When you write codes, it makes it a lot easier. So under the hood, it still does the same thing. It sends out a URL query to PubChem. So kind of right here, you can see, you're using kind of PubChem Pi, and then here you are looking up the actual PCP. So you kind of find the molecules in PubChem, and then you can kind of draw out the structure. You can see it's actually PCP here. So just kind of a nice little tool to have, and something I use a lot. So I thought it would be nice to tell you about this. And that's basically all I have, and I'll share the code later so you can take a look.
Right, thanks, Jason. Questions?
Hey, Jason, I have a question for you. So we found, if I recall correctly, that doing some of for the first section, doing some of the filtering in Reaxys itself or SciFinder, right, it is not particularly reliable, right? If you want to filter out primary amines, for example. Have you found that processing it the way you did via the RDKit and sort of in this Python notebook is sort of more effective?
Not sure how SciFinder does this, but I would imagine RDKit is gonna be pretty good because you know exactly what it is. I guess SciFinder, you don't really know how it does the filtering. Right. But I guess for this, primary means, I guess, depending on the specific things that you want to filter to, but I think, yeah, it shouldn't be a problem. And this is also kind of, yeah, I guess there's always a chance that it could, miss a few molecules, but I guess it always happens.
Yeah, I guess we had just seen, right, when we were doing some of the substrate scope, right, design, that the reacts, especially I think it was the reaxis filtering, was iffy in terms of sometimes you look back and you see it sort of actually excluded things that it shouldn't have, or that it missed things. So I'm curious if it makes more sense just to download the entire list then, if you can, and then apply the filters as you're doing it with this code.
Yeah, definitely. And also, this thing is because you can see the, whatever smiles and, smarts, you can actually see it. So if there's a molecule that you missed, you can kind of take a look and see what it is. And, maybe you can change the filter. And then if, for SciFinder, obviously it's a lot harder because it's just kind of just names and, you don't know what it actually does. Yeah, I would say this is probably better, more customized, if you will.
Certainly more transparent than all the stuff in SciFinder that kind of seems to be going on under the hood. They never tell you what they do. More questions? If that is not the case, and let's thank Jason again.